Imagine standing at the edge of existence itself, watching as everything you've ever known accelerates away from you. Not slowly, not gradually, faster and faster, pulled by something invisible, something that shouldn't exist. In 1998, two independent teams of astronomers pointed their telescopes at the dying embers of exploded stars scattered across the cosmos. What they found defied every prediction, violated every expectation, and shattered a century of carefully constructed physics. The universe wasn't just expanding, it was accelerating, being torn apart by a force that makes up nearly 70% of everything that exists, yet remains completely invisible, undetectable, and fundamentally incomprehensible. We call it dark energy, but that name is just our admission of ignorance wrapped in scientific language. Today, we journey through evidence that challenges everything we thought we understood about reality, about the fate of existence itself, and about whether the universe we inhabit is even stable. Prepare yourselves. We begin. The year was 1929, and Edwin Hubble was about to overturn humanity's understanding of the cosmos. Working with the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble measured the light from distant galaxies and discovered something extraordinary. They were all moving away from us, not just drifting, but fleeing, as if space itself was stretching between us and them. The universe was expanding. For decades, this discovery posed a profound question to physicists. If the universe was expanding, what would happen to it? Gravity, after all, pulls everything together. Every atom, every star, every galaxy exerts gravitational attraction on every other piece of matter in existence. Logic dictated that this cosmic expansion should be slowing down, gradually overcome by the relentless inward pull of gravity itself. Think of it like throwing a ball into the air. Gravity slows its ascent until it stops and falls back down. The universe, physicists reasoned, should behave the same way. Eventually, the expansion would slow, stop, and perhaps reverse into a catastrophic collapse, a big crunch that would end everything. By the 1990s, astronomers had the technology to test this assumption. They needed to measure exactly how much the expansion was slowing down. The key was finding cosmic objects that could serve as standard candles, objects whose true brightness was known, allowing astronomers to calculate their distance with precision. They found the perfect candidates in Type Ia supernovae. These catastrophic explosions occur when a white dwarf star accumulates too much matter from a companion star, triggering a thermonuclear detonation. The critical detail is that these explosions always happen at the same mass limit, about 1.4 times the mass of our Sun, known as the Chandrasekhar limit. This means Type Ia supernovae always explode with roughly the same intrinsic brightness, making them perfect measuring sticks for cosmic distances. Two teams embarked on this measurement independently. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams painstakingly observed dozens of distant supernovae, calculating their distances and measuring how fast they were receding from us. The expectation was clear. Distant supernovae, whose light left them billions of years ago, should appear closer than they would if the expansion rate had remained constant, because the expansion should have been slowing down over time. But when the data came in, both teams independently discovered something that seemed impossible. The distant supernovae were dimmer than expected, farther away than they should be. The universe hadn't been slowing down at all. It had been speeding up. The implications crashed through the physics community like a shock wave. Something was pushing the universe apart, overpowering gravity itself. Some force or entity pervaded all of space, causing the very fabric of reality to expand at an accelerating rate. The discovery was so disturbing, so contrary to expectation, that both teams initially questioned their own data. They checked for errors, recalibrated instruments, analyzed alternative explanations. Dust between galaxies could make distant objects appear dimmer, but detailed analysis ruled this out. Different types of supernovae could be contaminating the sample, but rigorous classification eliminated this possibility. Every conventional explanation fell short. The evidence was undeniable. In 1998, both teams published their findings. The universe was accelerating, driven by something utterly mysterious. Physicists dusted off an old term that Einstein himself had introduced and later abandoned. They called it dark energy. But the evidence forces us to confront an uncomfortable possibility. This mysterious force doesn't just exist. It dominates everything. To understand how completely dark energy dominates our universe, we need to take inventory of existence itself. When astronomers began cataloging the energy content of the cosmos, they discovered something profoundly disturbing. Ordinary matter, everything we can see and touch, all the stars and planets and gas clouds scattered across billions of light-years, accounts for less than 5% of the universe. Dark matter, the invisible gravitational scaffolding that holds galaxies together, makes up about 27%. The remaining 68% is dark energy. This invisible force doesn't just exist at the margins. It is the dominant component of reality, and we have absolutely no idea what it is. Scientists discovered the first direct evidence of dark energy's effects through careful measurements of the cosmic microwave background radiation. This ancient light, released 380,000 years after the Big Bang, when the universe first became transparent, carries within it a detailed map of the early universe. In 2001, the Wilkinson Microwave Anisotropy Probe began measuring this radiation with unprecedented precision. The temperature fluctuations in this ancient light revealed the geometry of space itself. If gravity alone controlled the universe's fate, space should curve inward on itself, forming a closed sphere. If the expansion precisely balanced gravity, space would be flat. The data revealed something remarkable. Space is flat to within 0.4 accuracy. But the amount of matter in the universe, both ordinary and dark, wasn't enough to make space flat. Something else had to be filling the cosmos, contributing to its energy density. That something was dark energy. The Planck satellite, launched in 2009, refined these measurements even further. It mapped the cosmic microwave background in exquisite detail, measuring temperature variations of just a few millionths of a degree. The data confirmed not just the existence of dark energy, but its precise abundance. Exactly 68.3 of the universe's energy density, with an uncertainty of less than 2. These weren't indirect inferences or theoretical predictions. This was direct measurement of the universe's composition, and it revealed that everything we understand makes up less than a third of reality. But here's where it gets strange. Dark energy doesn't behave like any form of matter or energy we've ever encountered. Normal matter and energy dilute as the universe expands, spread the same amount of gas across a larger volume, and its density decreases. Dark energy doesn't dilute. its density remains constant, even as space expands. This means that as the universe grows larger, the total amount of dark energy increases. New dark energy appears to fill the expanding space, maintaining constant density. The implications are staggering. Dark energy isn't just a substance permeating space. It appears to be a property of space itself. Astronomers found further confirmation by measuring the large-scale structure of galaxy distribution across the cosmos. The Sloan Digital Sky Survey mapped the positions of millions of galaxies, revealing how matter clustered over billions of years. Computer simulations showed how these structures should grow under different conditions. If dark energy didn't exist, gravity would have pulled galaxies together more tightly, creating denser clusters. But the observed distribution of galaxies matches predictions only when dark energy is included in the simulations. The accelerating expansion prevented matter from clumping as efficiently, leaving galaxies spread across the cosmos in precisely the pattern we observe. In 2005, scientists measured something even more specific about dark energy through a technique called baryon acoustic oscillations. In the early universe, pressure waves rippled through the hot plasma of matter and radiation, like sound waves through air. When the universe cooled enough for atoms to form, these waves froze into the distribution of matter, leaving a characteristic scale imprinted on galaxy clustering. Astronomers measured this scale in the distribution of galaxies at different cosmic epochs. The measurements revealed exactly how much the universe had expanded at different times in its history. The pattern matched predictions only if dark energy had been accelerating the expansion for the past 6 billion years. The acceleration wasn't constant throughout cosmic history. It began relatively recently, when the universe was about half its current age, and has been intensifying ever since. The most recent observations come from gravitational lensing studies. Massive galaxy clusters warp space-time around them, bending the light from more distant galaxies behind them. By measuring this distortion, astronomers can calculate how much matter exists in these clusters and how the universe's expansion has affected the paths of light rays traveling through space. Surveys like the Dark Energy Survey, which observed 300 million galaxies between 2013 and 2019, confirmed dark energy's existence through entirely independent methods. Every measurement, from every technique, points to the same conclusion. Dark energy is real, but this represents just one piece of a much larger puzzle hidden in the equations of physics themselves. The most remarkable discovery involves the sheer improbability of dark energy's strength. When physicists attempt to calculate how much dark energy should exist based on quantum field theory, they encounter what might be the worst prediction in the history of science. Quantum mechanics tells us that empty space isn't truly empty. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum for the briefest instance before annihilating. This quantum foam should contribute to the vacuum energy of space, creating what amounts to dark energy. When physicists calculate how much vacuum energy should exist, the answer they get is 10 to the power of 120 times larger than what we observe. That's not 120 times larger. It's 1 followed by 120 zeros times larger. The predicted value is so enormously greater than reality that it represents the most spectacular failure of theoretical physics ever recorded. Yet somehow, the actual value of dark energy is perfectly balanced to allow the universe we observe to exist. If dark energy were slightly stronger, matter would never have clumped together to form galaxies or stars. The universe would be a cold, diffuse fog of particles flying apart from each other. If dark energy were even slightly weaker or attractive rather than repulsive, the universe would have collapsed back on itself billions of years ago in a big crunch. The window for a universe that can support complex structures, let alone life, is vanishingly narrow. We exist in a cosmos where dark energy has precisely the right strength, for reasons nobody can explain. Recent observations reveal increasingly strange patterns in how dark energy behaves across different cosmic epochs. The Dark Energy Spectroscopic Instrument, which began observations in 2021, has been measuring the expansion history of the universe with unprecedented precision. It maps the 3D positions of millions of galaxies spanning 11 billion years of cosmic history. Preliminary results suggest something disturbing. Dark energy's strength might not be constant. The equation of state parameter, which describes whether dark energy behaves like Einstein's cosmological constant or something more dynamic, shows hints of variation over time. If confirmed, this would mean dark energy isn't a simple property of space, but something that evolves, something that changes its behavior as the universe ages. Scientists studying the cosmic microwave background have discovered anomalies that challenge standard cosmological models. The cold spot, a region of space about 1.8 billion light-years across, where the cosmic microwave background is slightly cooler than surrounding areas, has no conventional explanation. Some physicists speculate it might be evidence of another universe pushing against ours in the infinite expanse of the multiverse, creating a region where dark energy behaves differently. While highly speculative, the anomaly remains unexplained by standard physics. In 2019, a tension emerged in measurements of the universe's expansion rate, known as the Hubble constant. When astronomers measure the expansion rate using distant supernovae and other cosmic distance ladders, they get one value. When they calculate it from the cosmic microwave background and the known physics of the early universe, they get a different value. The discrepancy is small, about 9 parns, but it's statistically significant and has persisted through increasingly precise measurements. Something is wrong. Either our measurements are systematically flawed in ways we don't understand, or the universe's expansion history is more complicated than our models predict. Some physicists suggest dark energy itself might be responsible, perhaps evolving in ways that create this tension between early and late universe measurements. Theoretical physicists have proposed increasingly exotic explanations for dark energy's nature. Some suggest it might be quintessence, a dynamic quantum field that permeates space, similar to the inflaton field thought to have driven the universe's initial rapid expansion. Others propose phantom energy, a form of dark energy whose density increases over time, eventually growing so powerful it would rip apart galaxies, stars, planets, and even atoms in a Big Rip scenario. Still others suggest modifications to general relativity itself might explain the acceleration without requiring mysterious new energy forms. The most disturbing possibility comes from quantum field theory. Our universe might exist in a false vacuum, a temporary state of energy that appears stable, but isn't the true ground state. Dark energy might be the signature of this false vacuum, and at any moment, a quantum fluctuation could trigger a phase transition to the true vacuum. This transition would spread at the speed of light, obliterating everything in its path, rewriting the laws of physics themselves. We wouldn't see it coming. One moment the universe would exist as we know it. The next it would be replaced by something utterly different, hostile to the existence of matter as we understand it. The evidence extends beyond cosmic acceleration into the realm of fundamental questions about whether reality itself is stable. Einstein's general relativity provides the mathematical framework for understanding dark energy, but it also reveals how deeply mysterious it truly is. In Einstein's equations, dark energy appears as the cosmological constant, represented by the Greek letter lambda. Einstein originally introduced this term in 1917 to counteract gravity and allow for a static universe, consistent with the prevailing belief that the cosmos was unchanging. When Hubble discovered the universe was expanding, Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. Ironically, the 1998 supernova observations resurrected this abandoned concept. The cosmological constant is now the simplest explanation for dark energy, but calling it an explanation is generous. It's more like a placeholder, a mathematical term that describes what we observe without explaining why it exists or why it has the value it does. The cosmological constant possesses unique properties that distinguish it from all other forms of energy. It has negative pressure, meaning it pushes outward rather than pulling inward. This negative pressure is what drives the accelerating expansion. Think of it like anti-gravity, though that term is misleading because dark energy doesn't counteract gravity locally. It operates on the largest cosmic scales, becoming significant only across distances of billions of light years. Within galaxies, or even galaxy clusters, gravity remains dominant and dark energy's effects are negligible. But across the observable universe, dark energy's repulsive effect overpowers gravity's attractive pull. Leading physicists at institutions like the Institute for Advanced Study, the Perimeter Institute, and CERN have proposed competing interpretations of what dark energy represents. Steven Weinberg, Nobel laureate and theoretical physicist, suggested that the cosmological constant might be an example of anthropic selection. In a multiverse containing universes with every possible value of the cosmological constant, only those with values compatible with structure formation could contain observers to measure it. We observe a small cosmological constant not because physics demands it, but because only universes with small values can support life capable of asking the question. This explanation is both profound and unsatisfying, shifting the mystery from physics to metaphysics. Other researchers, including physicist Paul Steinhardt at Princeton, argue that dark energy isn't constant but dynamic. Steinhardt helped develop models of quintessence, where a slowly evolving quantum field drives the acceleration. In these models, dark energy's density changes over cosmic time, potentially explaining why we happen to live in an era when dark energy and matter have comparable densities. This cosmic coincidence, the fact that we observe the universe at a moment when dark energy has just begun dominating over matter, seems suspicious. Why should we exist precisely at this transition moment in cosmic history? Dynamic dark energy models offer potential solutions to this coincidence problem. String theory, the attempt to unify all forces of nature, including gravity within a single quantum framework, struggles to accommodate dark energy. String theorists work with landscapes of possible vacuum states, perhaps 10 to the power of 500 different possible configurations of extra dimensions and fields. Finding stable vacuum states with small positive cosmological constants that match our universe has proven extraordinarily difficult. Most string theory vacua predict either zero dark energy or catastrophically large values. The fact that we observe a small positive value places severe constraints on string theory models and might even suggest that string theory as currently formulated is incomplete. This forces us to reconsider fundamental assumptions about the relationship between quantum mechanics and gravity. Dark energy operates at the intersection of these two pillars of modern physics, and their incompatibility becomes glaringly obvious when we attempt to understand vacuum energy. Quantum field theory predicts enormous vacuum energy. General relativity describes how energy warps spacetime. Yet somehow, these enormous quantum fluctuations don't gravitationally curve space into oblivion. Some unknown mechanism cancels them to 120 decimal places, leaving only the tiny residue we observe as dark energy. Understanding this cancellation mechanism could be the key to developing a quantum theory of gravity, the holy grail of theoretical physics. Physicist Sean Carroll at Johns Hopkins University has explored whether dark energy might indicate that space-time itself is emergent rather than fundamental. Perhaps space and time aren't basic features of reality, but arise from some deeper quantum structure. In this view, dark energy might be a clue about the true nature of space-time, a hint that our understanding of space as a smooth continuum breaks down at the deepest levels. The acceleration we observe could be an artifact of this deeper structure, emerging from quantum entanglement patterns or information-theoretic principles we don't yet grasp. The quest to understand dark energy has driven an unprecedented international scientific collaboration. Multiple space missions and ground-based surveys are now mapping the universe's expansion history with ever-increasing precision. The European Space Agency's Euclid mission, launched in 2023, is designed to map the geometry of the dark universe across 10 billion years of cosmic history. Its instruments measure the shapes of billions of galaxies, tracking how gravitational lensing by dark matter and the expansion driven by dark energy have evolved. The data will reveal whether dark energy's strength has changed over time or remained constant, potentially distinguishing between the cosmological constant and more exotic alternatives. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will survey hundreds of millions of galaxies, measuring their distances with unprecedented accuracy. It will detect thousands of Type Ia supernovae at varying distances, tracing the universe's expansion rate across different epochs. Combined with measurements of baryon acoustic oscillations and weak gravitational lensing, the Roman telescope will constrain dark energy's properties to within a few percent, potentially revealing subtle variations that current observations can't detect. The Vera Rubin Observatory in Chile, which began operations in 2024, conducts the Legacy Survey of Space and Time, the most comprehensive survey of the night sky ever attempted. It will image the entire visible sky every few nights for 10 years, detecting billions of galaxies and millions of transient events like supernovae. The sheer volume of data will enable statistical precision impossible with smaller surveys, potentially revealing subtle signatures of dark energy's evolution or interactions with other cosmic components. Recent breakthroughs suggest entirely new approaches to probing dark energy. Gravitational wave observatories like LIGO and Virgo detect ripples in space-time from colliding black holes and neutron stars. These gravitational waves travel across the universe at the speed of light, and their properties can reveal how space has expanded during their journey. When combined with electromagnetic observations of the same events, astronomers can measure cosmic distances and expansion rates independently of traditional methods. This provides a crucial cross-check on supernova measurements and helps resolve tensions in Hubble constant measurements. The James Webb Space Telescope, operating since 2022, has begun observing the earliest galaxies in the universe, formed just a few 100 million years after the Big Bang. These observations constrain how quickly structure formed in the early universe, which depends on the balance between gravity and dark energy. Webb's ability to peer deeper into cosmic history than any previous telescope allows astronomers to test whether dark energy behaved differently in the universe's youth compared to today. Theoretical developments point toward laboratory experiments that might probe dark energy directly. While dark energy's effects are negligible at small scales, extremely precise experiments might detect tiny deviations from standard physics caused by the vacuum energy associated with dark energy. Experiments searching for variations in fundamental constants, like the fine structure constant, could reveal whether dark energy couples to other fields in ways that cause constants to drift over cosmic time. Atom interferometry experiments on Earth and in space might become sensitive enough to detect dark energy's influence on atomic energy levels. What this means for us extends beyond academic curiosity. Understanding dark energy determines our ability to comprehend the universe's ultimate fate. If dark energy remains constant, the universe will continue accelerating forever, eventually entering a phase called the Big Freeze. Galaxies beyond our local group will recede beyond the cosmic horizon, their light red-shifted into invisibility. The universe will become increasingly cold, dark, and empty, with matter spread across ever larger volumes until the final stars burn out and black holes evaporate through Hawking radiation. This process will take trillions upon trillions of years, but it represents the heat death of the universe, the end of all structure and complexity. If dark energy is phantom energy whose strength increases over time, the universe faces a more violent end. The Big Rip scenario envisions dark energy growing so powerful that it eventually overcomes not just gravity, but all forces holding matter together. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets, then molecules and atoms themselves. Even atomic nuclei would be ripped apart in the final moments before the Big Rip. The time frame for this scenario depends on how quickly phantom energy strengthens, with estimates ranging from 20 billion to hundreds of billions of years in the future. Alternatively, if our universe exists in a false vacuum, the future could be far more uncertain. Quantum tunneling to the true vacuum could occur at any moment, though the probability of this happening in any given time frame is vanishingly small. If it does occur, a bubble of true vacuum would nucleate somewhere in space and expand at the speed of light, converting everything in its path to the new vacuum state with potentially different physical laws. This vacuum decay scenario isn't just the end of our universe, but the end of physics as we know it. The forces, particles, and structures we depend on would cease to exist, replaced by something utterly alien. The most mind-bending implications emerge when we consider dark energy's relationship to the nature of reality itself. If dark energy is indeed the energy of the quantum vacuum, then empty space isn't empty at all, but seethes with energy at the most fundamental level. Every cubic centimeter of space contains this irreducible energy, and while its density is tiny, about 6 atoms worth of energy per cubic meter, its total dominates the universe because space is so vast. This means reality is primarily composed of empty space filled with mysterious energy rather than matter and radiation. We are not the universe's primary constituents, but rare excrescences on an ocean of dark energy. The anthropic implications of dark energy raise profound questions about whether we inhabit one universe among many. The multiverse hypothesis suggests our universe is just one bubble in an eternally inflating cosmic foam, where each bubble universe has different physical laws and constants determined by how symmetries break during inflation. In most universes, the cosmological constant would be vastly too large or too small to permit structure formation. We observe a habitable value not because it's typical, but because only such universes can support observers. This explanation trades the mystery of fine-tuning for the assumption of infinite universes, most of which are sterile and lifeless. Whether this represents progress or merely relocates the mystery remains hotly debated. Some physicists speculate that dark energy might provide clues about physics beyond the standard model. Supersymmetry, the proposed symmetry between matter particles and force carriers, predicts that every known particle has a heavier supersymmetric partner. If supersymmetry exists at high energies, it could help cancel the enormous vacuum energy predicted by quantum field theory, explaining why dark energy is small rather than catastrophically large. The Large Hadron Collider has searched for evidence of supersymmetric particles without success, but higher energy colliders might yet reveal this hidden symmetry. If supersymmetry is found, it would suggest dark energy's value is protected by symmetry principles we're only beginning to understand. The holographic principle, emerging from black hole thermodynamics and string theory, suggests that the information content of any region of space is proportional to its surface area rather than its volume. This bizarre idea implies that three-dimensional space might be a holographic projection of information encoded on a two-dimensional boundary. Dark energy plays a crucial role in holographic cosmology. The cosmological constant determines the size of the cosmic horizon, the ultimate boundary beyond which we can never receive information due to accelerating expansion. Some theorists propose that dark energy is intimately connected to this holographic limit, suggesting that the accelerating universe is fundamentally a holographic phenomenon. Reality itself might be a projection, with dark energy representing the canvas on which existence is painted. Questions about dark energy intersect with the simulation hypothesis, the idea that our universe might be a computational construct running on some advanced civilization's hardware. If reality is simulated, dark energy could be a computational trick to limit the simulation's scope. By accelerating the expansion and creating a cosmic horizon, dark energy ensures that the simulation only needs to render a finite volume of space in detail. Regions beyond the horizon could remain uncomputed, saving resources. While highly speculative, this perspective illustrates how dark energy forces us to question the fundamental nature of existence itself. The connection between dark energy and quantum entanglement has begun attracting theoretical attention. Entanglement links quantum particles across arbitrary distances, creating correlations that Einstein called spooky action at a distance. Some physicists propose that space-time itself emerges from entanglement patterns, with the smoothness of space reflecting high levels of quantum entanglement. Dark energy might affect these entanglement patterns, perhaps gradually decreasing quantum correlations across cosmic distances as space expands. If this connection exists, understanding dark energy could unlock deep truths about the quantum nature of space-time. The most profound implications emerge when we consider consciousness and observers. The anthropic principle suggests our existence as conscious observers places constraints on physical constants, like the cosmological constant. But this raises the question of why consciousness exists at all, and what role, if any, observation plays in determining physical laws. Some interpretations of quantum mechanics suggest that observation collapses quantum wave functions, selecting classical outcomes from quantum possibilities. If dark energy is related to quantum vacuum fluctuations, could the act of observation somehow stabilize the vacuum, preventing transitions to other states? This borders on speculation, but it highlights how dark energy intersects with the deepest mysteries of quantum mechanics and the role of observers in physics. Dark energy might hold the key to resolving the black hole information paradox. When matter falls into a black hole, quantum information seems to be destroyed when the black hole eventually evaporates through Hawking radiation, violating quantum mechanics' principle that information is conserved. Some recent proposals suggest that the quantum vacuum associated with dark energy might store this information, encoded in subtle correlations spread across space. The accelerating expansion driven by dark energy might even be related to the rate at which information escapes from black holes, connecting cosmology to quantum information theory in unexpected ways. We have journeyed through evidence that reveals our universe is dominated by something we cannot see, cannot touch, and barely understand. Dark energy shapes the cosmos at the largest scales, determines the ultimate fate of existence, and challenges our deepest theories about the nature of reality. We began with the shocking discovery that the universe's expansion is accelerating, driven by something that makes up more than 2/3 of everything that exists. We traced how multiple independent observations confirm this mysterious force, from the cosmic microwave background to the distribution of galaxies across billions of light years. We confronted the staggering improbability of dark energy's precise value, and the profound questions this raises about whether our universe is one among countless others. What we've learned is both humbling and exhilarating. Humanity has discovered that we understand less than 1/3 of the universe's composition. The remaining majority remains shrouded in mystery, accessible only through its gravitational effects and its influence on cosmic expansion. Yet, within this ignorance lies opportunity. Dark energy represents one of the greatest puzzles in science, potentially holding the key to quantum gravity, the nature of space-time, and the ultimate questions about why existence takes the form it does. The current scientific consensus is clear. Dark energy is real. Its effects are measurable, and understanding it requires new physics beyond our current theories. But consensus also acknowledges profound uncertainty about what dark energy actually is. The next decades will bring unprecedented observational capabilities. We will map the universe's expansion history with exquisite precision, potentially revealing whether dark energy evolves over time or remains constant. We will probe deeper into cosmic history, examining how structure formed in the early universe and how dark energy's influence has grown. These observations might confirm the cosmological constant as the correct description, or they might reveal something far stranger, a dynamic field that evolves, interacts, and shapes reality in ways we haven't imagined. Either outcome would transform our understanding of the cosmos. The quest to understand dark energy embodies humanity's deepest drive to comprehend our place in the universe. We are fragile collections of atoms, briefly aware, contemplating forces that dwarf galaxies and phenomena that span billions of years. Yet we persist in asking questions, building instruments, and seeking understanding. Dark energy reminds us that the universe is far stranger than we imagined, that reality contains depths we've only begun to plumb. As we peer into the darkness, seeking the invisible force that shapes everything, we are engaged in the most profound exploration possible, the attempt to understand existence itself. The universe is vast. The mysteries are endless. The journey continues,